subtract them, multiply them, divide them. Now we're going to do something a little more complicated and really important called composition. Functions. Composing two functions. The idea is you take a function and you take g of x equal to x squared, and we're going to take it from some domain whose range. So this will be 1, 4, 9. And then we're going to take the range, the elements in the range, the images, and we're immediately going to plug them into another function, f of x. In this case, we're going to just use x plus 1. We're going to call this a new. We're going to give this a new name. This is h of x. Write this f of g of x, the composition of g and f. Another way we might write it, slightly different notation, so we'll use a little circle here, f g of x. I probably won't write it this way, but you'll see it this way in the book. So another way of thinking of this is I have some function, h of x, which is a machine, takes in an x. And first thing it does is it runs it through this function g, right? And then the output of g goes into f, and then that's what I get out. Well, all right. When you're dealing with algebraic expressions and you combine two functions this way, we can merge these algebraic expressions. So how would we do that? We want to find f of g of x. Well, f of x takes its independent variable and adds 1 to it. So that's this g of x plus 1. G of x takes its independent variable, sets it to x squared, so that's x squared plus 1. This brings to mind an important point. You have to be careful that you don't do this in the wrong order. Instead, I was to say g of f of x, that's a different function. It's a different composition. So what would that be? Well, g is going to take its independent variable, square it. F of x is going to take its independent variable to x plus 1. And that's x squared plus 2x plus 1. Definitely not the same thing. So you do want to take care when you're composing that you compose it the right way. So let's just look at this first example for a second. Let's think about the domains and ranges of these two functions, g and f, and the result. So again, f of x is x plus 1. So the domain of x plus 1 would be what? That's someone from that back row over there. What's the domain of x? F of x equals x plus 1. What values of x can I plug into that function? Anybody?
Everything?
All values?
All values, yeah. All reals. Yeah. Okay. How about its range? How about this second row here? Tell me what the range of that function is. Yeah? Speak so the whole class can hear you. Negative infinity to infinity, or all reals? All reals. Okay, good. But what about our g of x? What's the domain on that? That's someone from, where shall I put? Jake, from your row. That doesn't mean you. Just please. Yeah.
All positive integers?
Yeah. Oh. Okay, so the domain is all positive integers.
Oh no, that would be the range. It would be all real numbers.
All real numbers. Good. Okay. I know you know the answer to the next question, so don't answer. Okay. What's the range on that?
Natural numbers. Natural numbers.
Okay, so you're thinking
They're all positive.
positive numbers, right? Yeah, okay, now remember the natural numbers are just 1, 2, 3, you know.
Like including zero.
But remember I can put any real number in. I can put in a half. I mean, you're right, it's going to be positive and 0, but you're missing all the ones in between.
It's from 0 to infinity.
Yeah, it's greater than equal to 0, let's say. Do you see what the distinction I'm making? Yeah, it's just, I mean, it's important. Sometimes you'll have a domain, you'll have what we call a discrete function, where the domain is just integers and the output is also integers. Okay. All right, so what happens? Our f of g of x is x squared plus 1. What's the domain on that? This is easy. Somebody. All reals, okay. But what is the range?
Greater than 1.
Greater than 1. Greater than or equal to 1, yeah. Okay, so let's think about, you know, what can happen here, right? We have a domain that goes into G, and the output is its range, right? So that range is the maximum domain we can put into F for our new function. Now there might be values in the domain of G that don't fit into F. So now we have to take those off the domain of, you know, their pre-images, as we call, and we have to take them off of G. In other words, let's say f of x was 1 over x minus 1, and g of x is just, we'll make it real easy, it's just x. So 1 was in the domain of G, but we have to remove it from H because then we get something defined here. So I guess the point I'm trying to make is you have to be really careful about the domain and range of your new function. May get decreased. The range may really doesn't really seem to have much to do with either of these functions, does it? Let me give you an extreme example. My f of x is negative x squared. A g of x is the square root of x. And I want to know what g of f of x is. Okay. Well, okay, let's find the, well, let's look at these first. So the domain on f of x is, of course, still all reals, right? You can plug in any value. The domain on g of x is not. It has to be greater than or equal to 0. The range on this is negative numbers and 0. The range on this is positive numbers. Okay. So let's find the algebraic expression for the rule for h of x. So that's square root of negative x squared. Okay. What happened to the domain and range of this? What's the domain on this?
0.
It's just 0. Who said that? Thank you. Yeah, it's just 0. The domain of h is just the set with 0. And therefore, the range is just 0, yeah. So this is an extreme example. When you compose functions, sometimes you have to think a little bit about the domain and range because funny things happen. Okay. We should do one other example here before we're done with this. I have functions f of x equals x cubed and g of x square root of x minus 3. And I'm interested in both compositions, f of g of x and g of f of x. So, okay. F of g of x, well, g of x is my independent variable, so that gets cubed, right? That just becomes square root of x minus 3 cubed. And here f of x is my independent variable for g of x. So that becomes x cubed. Becomes square root of f of x minus 3 equals square root of x cubed minus 3. Okay, those are pretty different. What's the domain on this function? It's a little trickier, isn't it? We need what's under the radical to be greater. Yes, Midori?
I was going to say x is greater than or equal
Yeah, absolutely. X is greater than or equal to 3. Okay, so if x is greater than or equal to 3, what happens here? We can get, what kind of values do we get out of the square root? We get positive values. So when we cube them, we're just going to get, our range is going to be greater than or equal to 0. Right. Someone in Kenny's row, what's the domain on this function? This is the hard problem of today, so it's really good if you get this. No? Some other team want to kind of jump in here?
Is it greater than or equal to 1? I mean,
X is greater than,
well, not 1, but
not 1, okay. Well, if it was 2, right, certainly 8 minus 3, that's all good. But that's not all of it, is it? Right? What do I want? I want x cubed minus 3 to be greater than or equal to 0, right? So how do I get that to happen? Well, x cubed is greater than or equal to 3. Can I just find the cube root here? Both sides? We didn't really talk about this that much. Cube roots don't change the sign, do they? So that's actually going to be fine, right? Cube root of x cubed greater than or equal to cube root of 3. Or x greater than or equal to cube root of 3. With x squared, it's a little different, right? It's x squared greater than 3. Then you can have negatives also. All right. So that's x greater than or equal to cube root of 3. All right, what about the range on that? Jump right in. I'll let you think about it for a minute. I'm going to think about what I'm doing. We're gonna have a quiz on. We're going to ask questions about the range on things. What values can I get out of this? What kind of values? Positive, okay. So greater than 0. Is that all? And 0. Okay, good. All right. I guess the last part of this problem is it's too easy. We'll do it anyway. So, so what is f of g of 4? And what's g of f of 4? Well, f of g of 4, 4 minus 3 is 1, square root of 1 is 1, 1 cubed is 1. Square root of x cubed minus 3, I plug in 4, 4 cubed is 64, minus 3, square root of 61. So again, you know, two functions where the order of the composition is crucial. Right. Any other questions about composition of functions? I just had kind of a brainstorm. You know, you might think, well, why are we learning this? You know, well, you take two functions and plug one into the other and we'll get a new function. I don't think this will come up in this class, although it might. But sometimes you have a complicated expression like, cubed over square root of x minus 5 over, we'll get there, log of x, something like that. And just dealing with it in this form, sometimes it's difficult. But if we can break it down, let's say, let's call this f of x, and we can then say g of x equals square root of x minus 5, h of x equals log of x, k of x equals x cubed. Now we can kind of make it at least a little simpler. Now it's just g of x over h of x k of this, right? I mean, sometimes that comes up. In calculus, it comes up a lot, where you want to separate functions somehow so you can do something nice with it. Okay, that's something that jumped into my head out of nowhere. All right. Next topic is something called a one-to-one function. We're going to talk about what a one-to-one function is. And we're also going to see an example of why they're important. It's important to know what a one-to-one function is. Okay, here's a simple example. F of x equals x plus 4. So if I were to look at some values, okay, so here's my domain, and what does f of x do? It takes 1 to 5, it takes 2 to 6, it takes 3 to 7. What makes this a one-to-one function is the image of each of these, right? The element in the range that you get to from f of x. Each of these is unique. That is, there's no other value here that will also go to 7. Here's a counterexample. Let's take a look just for a second at f of x equals x squared. Well, just going to pick some numbers in the domain. And what happens? Well, 1 goes to 1, that's good. 2 goes to 4. But minus 2 also goes to 4. So this is an example. This is not a one-to-one function. Now, we have a very precise way to say this in mathematics. What we can say is, if f of x is 1-to-1, and x1 and x2 are members of the domain, then f of x1 equal to f of x2, that implies that x1 equals x2. In other words, if you apply this function to two values and you get the same thing, it's because you started with the same value in the domain. There's another good way to state this definition, but before I do, let me ask, does everyone not recall from geometry what a contrapositive is. Maybe you had it and forgot. Anybody? Okay. All right. So when you're dealing with theorems, theorems look like, if A, then B. And the contrapositive of this statement looks like this. If not B, then not A. As surprising as it might seem, these two are always equivalent. They mean the same thing. See if we can think of an example. I should come up with these examples before I come to class, or it'll take me a long time to think of them. Okay, this is simple. If x is greater than 0, x squared is greater than 0. Okay, just think of what the negation of x squared greater than 0 is. If x squared is not greater than 0, x squared is less than or equal to 0. And what's the negation of this? Then x is less than or equal to 0. Well, if this is true, then this must be true. Right? Is that true? X squared is less than or equal to 0. Well, that would be x is 0, right? Then this is true. And x is less than or equal to 0, because x is 0. Okay, we're not going to go into that today. That could be a whole class when we talk about talking about logic. But the point is, another way to state this is if f of x is 1 to 1, x1 not equal to x2 implies f of x1 is not equal to f of x2. So that's another way to think of a 1-to-1 function. You start with different values, you get different values. All right, I'm going to do something I'm not going to do much of in this class. This is mathematics, and what mathematicians do all the time is they prove things. And so I'm going to show you a simple proof. Show you a proof, I have to have a theorem, right? So my theorem is f of x is equal to ax plus b, a and b being constants, and f of x is 1-to-1. Okay. How would I go about that? I'm going to use this definition of a 1-to-1 function. And I'm going to say let x1 and x2 be, remember, the domain of f. And assume f of x1 equals f of x2. So that's the implication part of this. I'm going to take this and try and show you that x1 and x2 have to be equal. Okay? It's not really very hard. F of x is ax plus b, so f of x1 is ax1 plus b. And f of x2 will just be ax2 plus b. Well, I can subtract b from both sides of this and get ax1 equals ax2. And I can divide both sides by a. And now I have x1 equals x2. Which is what I needed to show that this was a one-to-one function. I want to look at one-to-one functions from a visual point of view, a graphical point of view. So first, let me put up this function f of x equals x cubed. And let's take a look at that. This is a function that is one-to-one. And I want you to compare it with another function, f of x equal x squared. It's of course a parabola. And this is not one-to-one. Okay, I want to look at these two, and now I want you to think for a minute. Is there something I can look at on the graph that tells me right away that this is definitely not a one-to-one function? Yes, Selena?
If you have symmetry along the y-axis, it shows you that it cannot be a one-to-one function because it's reflected. So it means on both sides you have the same y value but multiple x values.
Okay, I'm going to just, that was very good. I'm going to simplify that. It doesn't matter that it is symmetric. It doesn't matter that it's symmetric. What matters is a y value here. If it was symmetric, this has to be true. But it could be true even if it wasn't symmetric. We have a y value here and a y value here that are the same. But they come from, we'll call this x1 and x2. This is f of x1 and f of x2 are equal, but x1 and x2 aren't equal. So it's not one-to-one. We have a name for doing this. This is called the horizontal line test. This is not to be confused with the vertical line test. The vertical line test tells us whether it's not a function at all. This tells us, the horizontal line test tells us whether it's a one-to-one function or not. The horizontal line crosses 2 points on the graph, it can't be one-to-one. Now we look at this function on the other hand, and kind of in your head you draw infinitely many horizontal lines, and you'll see they're always just going to intersect at one point. So this passes the horizontal line test. All right, there's actually one other, pearl of wisdom one can figure out here about one-to-one functions. Notice something else different about these two graphs. So kind of goes like this. This one kind of goes like that. So there's some property of these two that's different. It seems related. I'm not being subtle here. All right. This is just increasing, right? So I have a function, and it can be increasing, but then it decreases, and then it increases. What's going to happen? It's going to fail the vertical line test. We talked about functions that increase on an interval. Now, it could go the other way too, right? It could just be decreasing. Right? That would work. It's a nice one-to-one. We know all lines are one-to-one functions, right? Actually, when we talked about increasing functions, I think what we said is that if x1 is greater than x2, greater than x2, then f of x1 is greater than or equal to f of x2. This is an increasing function, but we have to get to that equal. You could have a function that looks like this. Go up, increase, and it just goes straight across and it goes up again. It doesn't pass the vertical line test, so we have to remove this. This is called a strictly increasing function. There's no equal here. And similarly, you could have a strictly decreasing function. And the pearl of wisdom here is it's one-to-one. It's either increasing or decreasing. Well, actually, I've gone outside of my bounds here. All these functions have something else in common. They're all what we call continuous functions. They're not broken up. If you had a piecewise function, it could still be one-to-one, but it might not be decreasing everywhere. So, my statements about increasing and decreasing have to do with a continuous function. All right. Yeah, good thing. Okay, so let's take a look at this function again, which is not a one-to-one function. Oh, I'm sorry. Erased the wrong one. No. Is there anything I could do that would make this a one-to-one function? I just kind of erase this. What did I do? I changed the domain, right? Domain is now x greater than or equal to 0. Now it's increasing, and it's also one-to-one, right? So sometimes you can take a function that's not one-to-one, and you can make it one-to-one. this is really important. We're going to see why when we cover the next subject. Okay. Any questions about one-to-one functions before we go on? All right. We are now going to talk about something called an inverse function. It's an inverse function. Well, say I have some function. Say it takes these values, 1, 2, 3, values 5, 6, 7. This could be, again, x plus 4. Well, I might have another function that now takes this range as a domain and takes 5 to 1, 6 to 2, 7 to 3. In other words, it takes these values 1 that the original function set to 5 and sets them back to where they came from. We call this an inverse function, and the notation we typically use is, say, f minus 1 of x, f inverse of x. Now you want to be careful about the context. In a different context, f minus 1 of x would be what we would mean by 1 over f of x, right? That's not what we mean here. We mean the inverse function is the function that takes the x values, takes the range values f of x back to x. Okay. This example here is pretty easy to see what the inverse function, what the rule would be. If f of x is x plus 4, how do we get back to where we started from? What would f inverse of x be? Yes?
X minus 4. X minus 4.
X minus 4. That's pretty obvious, right? Let's take something just a little more complicated. Let's take f of x equals 2x plus 6. And I'm going to show you a strategy for finding the inverse function rule that works pretty well. First thing is, let's write this as y is a dependent variable, and of course x is the independent variable. Step 1. Now, what I want you to do is switch the x and y variable. So now I have x equals 2y plus 6. And now, we switch the independent and dependent variables. And now I want to solve for y. So that's pretty easy. subtract 6 from both sides. And let's divide by 2. And I'm going to put y back over here. And this now is my inverse function of x. Okay, let's check that. Let's see if that makes any sense. Let's pick the value of x. Let's say 0. It's easy to compute, right? So f of 0 is 2 times 0 is 0 plus 6 is 6. Okay. Well, what should the inverse function do? Inverse of 6. What is the inverse function of 6 do? 6 minus 6, that's 0, divided by 2 is 0, is 0. It's exactly what I wanted to do. I wanted to get back to my original x. Okay, let's try another one. Let's try y equals x squared. The domain being, right, I have to specify this because remember I need a one-to-one function, find an inverse. Domain from 0 to infinity. Well, say f of x. So again, I write this with an independent and dependent variable. And now I switch them. So x equals y squared. Now I want to solve for y. Well, that's just y equals square root of x. I don't have to worry about plus or minus because I know all my x's have to be greater than 0, right? So, say that right? I don't know if I said that right. I don't have to worry about my domain here. Okay, so my inverse function is the square root of x. And of course, that's exactly what you would expect. If I plug in some value, I'm going to square some value here, right? Say 2. 2 becomes 4. The inverse of 4 is 2, and I'm back to where I started from. I think I left out a really important point here. If you have a one-to-one function, then you have an inverse. And if you have an inverse function, your original function has to be one-to-one. All right. I want to go back again to this idea of looking at this graphically. Let's take these two examples here. F of x equals 2x plus 6, so my y-intercept, and it says slope 2. Oh, so that's going to be up here like this. And I got to put this into slope-intercept form, right? 1/2 x minus 6. Oh, no, not minus 6, minus 3. Okay. 1, 2, 3, and that has a slope 1/2, so that's down here, here. All right, that's my f and my f inverse. And then also let's look at this other function, f of x x squared kind of looks like this. And square root of x looks like this. Right? What do you notice about those two graphs? There's something we can say about them. Something that kind of sticks out. Yes, Martha. You're a mirror. Is that what you were going to say? Yeah. Remember when we were talking about mirrors, I said, you know, you don't necessarily have to have the axes in the mirror. If I draw a line along here, you can see that these two functions are mirrors of each other. Same with this function here. What is this line here? This line is y equals x. Now think about how I was creating these inverse functions. Switch the y and x variables, right? That's the same as, you know, taking the x-axis and the y-axis and flipping them over. So this is really the same thing. We get our inverse by switching y and x, mirroring over this y equals x. Question about this? Right. Property of all inverse functions. There's one more important feature of inverse functions that you should know about. Well, we know that if you take f of x and then you apply the inverse to that, you're just going to get back x. Better. So, when we were talking about f of x equals 2x plus 6, and f inverse of x is x minus 6 over 2. So if I were to check that out, right? So f inverse, okay, so I have to plug 2x plus 6, that's my f of x, into f inverse, minus 6 over 2. Well, that's just 2x over 2 equals x. Okay, we expected that. But in addition, you're going to find that f of f inverse of x will also be equal to x. In other words, if I start over in my range of f of x, some value, the inverse, I get back to some x, and I find f of x of that, I'm going to go back to where I started. So let's check that out here just for this example. I'm going to plug f inverse of x into here, so that's 2 times x minus 6 over 2 plus 6. Okay, what's that? These cancel. X minus 6 plus 6 equals x, just as I suspect. It's an important feature of inverse functions. F of f minus of x will equal f inverse of f of x equals x. Right, I think that's all I have. I want to say, I think there's an assignment out on on my website has the wrong date. The next assignment will be due next Friday. I don't want you guys to worry about it over the weekend, worry about being prepared for the exam. And I'm going to update that assignment. So, okay. Also, as I said, I'm going to be here in my office a lot today. If you have questions, you want to come by.